So, chapter 4, we're dealing with exponential and logarithmic functions. These are actually really nice for derivatives. They seem a little scary at first, but they're really straightforward. And when they come up for integrals, which is where we're headed next, you're always happy because they have nice integrals. They're nice to work with. I am assuming you have gone through either the other chapter 4 exponential sections, which should be a review to you, or this is familiar, how to work with exponential and logarithmic functions. If it's not, please go look through those other sections. Or I know Khan Academy has some really great, walkthroughs on how these work. So, and to save time, I'm going to skip those. If you want me to talk about them, message me and we can come up with a time. But anyway, let me get some of the stuff off my screen. There we go. Nope, go away. So our exponentials are the e to the x type function. Logs are the inverse of that. So our log functions, natural logs. The derivative of e to the x is e to the x. Like I said, they're kind of nice. If you have a function instead of just an x up there, you take, so if you have e to the u, where you use another function, it's the chain rule. So you take the derivative of u times e to the u. So a couple examples. Let's find the derivative. Can I see blue? Okay. So f prime of x. All right. So I take the derivative of this dude here, which I know is negative 12x to the third. And then my function as is. If you hear my child, I think he's playing Smash Bros in the other room. If you want to play Smash Bros with my child, please let me know. I'll hook you guys up. He's 13. Anyway, so that's that. We could clean this up a little bit, or we could just leave it. I'm going to leave it. That's good enough. Okay. Oh, good. I have some more fun ones here. Our next one is we have quotient rule. Words are hard today. So f prime of x equals. All right. So you remember our quotient rule. We take the derivative of the top times the bottom minus the top as is times the derivative of the bottom all over bottom squared. Hopefully you remember that. If not, that's what it is. So the derivative of the top is just the derivative of e to the x is e to the x. The derivative of 1 is 1. So actually it's 0. Oh, brain. So it goes away. Times the bottom minus the top times the derivative of the bottom, which is again e to the x, all over the bottom square. And I should have left myself enough space. E to the x times e to the x is e, add my exponents to the 2x minus e to the x minus e to the 2x minus e to the x all over, whoosh. Whoops, I forgot my square in there, didn't I? Sound effects help. Yes, thank you. Which is just negative 2 e to the x all over e to the x minus 1 quantity squared. So if you need to kind of take the derivative of the top and bottom off to the side, I do that sometimes too. So derivative of the top is just e to the x. The derivative of the bottom is just e to the x. That makes this calculation a little cleaner. And that's all we have to do with that one. This one we can't even clean up that much, so we're just going to leave it. Oh, good. Okay, our next one is we can do implicit differentiation with this. So we're combining all sorts of things. So remember, every time we take the derivative of the y, we either write y prime or dy dx. I think I will dy dx this time. So, product rule. The derivative of the first is 2x times the second plus the first times the derivative of the second. So derivative of y is y prime or dy dx minus, okay, the derivative of the inside. It's a y, so we write down dy dx e to the y. The derivative of -4 is 0 equals 0. This is kind of gross, but that's okay. We can deal with that. All right, so x squared dy dx minus dy dx e to the y equals -2xy. Factor out of dy dx. And finally, we want to solve for that dy dx, and I just barely have enough space. So I'm going to divide both sides by x squared minus e to the y. So I get dy dx equals -2xy all over x squared minus e to the y. That's our final answer. So really the derivatives of the e to the y by themselves are pretty straightforward. They're, as derivatives go, they're very kind to us. Where things get a little interesting is where we throw everything else with it. So that is that. Okay, derivative of our natural log. So natural log is the inverse of e to the y. We can do derivatives of regular logs or log base anything else, and I will show you those at the very end, but it really works the same way. And in calculus, most of the time you want e's in natural logs because it makes life easier. They're simpler derivatives. And then when we go to integration, this is what we're going to use, not base anything else. So if we just have natural log of x, its derivative is 1 over x. If we have natural log of u, so u is some function, we take the derivative of u, the inside, over u. So again, pretty straightforward. Okay, let's take the derivative of this bad boy. Okay, so the derivative of the inside of our natural log, so the derivative of 5x is just 5 over the inside. We can clean that up, and it's just going to turn into 1 over x. There's a reason. If you remember your logs, we're multiplying two things inside of our natural log, we can split it up into natural log of 5 plus natural log of x. So this is the sections we didn't talk about, but hopefully are familiar to you. So now, if we take the natural log of 5, the derivative of the natural log of 5, we just get 0 and 1 over x. So that's why it goes away. And we can use the spreading out our natural logs to make our math easier. And actually 1 or 2 down, I do believe I gave one of those to work on. Oh, look at that, I did. Okay. Now, there's one way to make this easier, excuse me. We can bring our x up and make it negative, and now we have the product rule instead of the quotient rule, but it's going to get us to the same place. I'll do it this way. I like the product rule better. Okay, the derivative of the first is -x to the -2 times the second plus the first times the derivative of the second. I should have done this the other way, but that's okay. So I get negative natural log of x over x squared plus 1 over x squared, which gives me 1 minus natural log of x over x squared. That should be right. Hang on, let me dribble to the top times the bottom minus the top times dribble to the bottom all over. Yeah, okay. It seemed weird. I just wanted to double check that it was good, and it is. So yeah, the hard part of this one was the product or quotient rule. All right, this last one looks terrible. I'm not gonna lie. I look at that and say, no, I don't want to do that. But we can use our rules of logs to make this easier. So the two rules we're gonna use, let me do this in pink. So the product, so natural log of a plus, or a times b, is natural log of a plus natural log of b. And then our exponent rule, natural log of a to the b, we can bring our b out front. So it's b natural log of a. So first thing I'm going to do is not take a derivative, is I'm going to simplify this madness. Oh, we're using black again. All right, so we have two things we're multiplying. I get natural log of x plus natural log of x squared plus 1 quantity squared. Can simplify one more time. We'll go sideways. Natural log of x plus 2 natural log of x squared plus 1. Now, if you're like me back in my calc days, I would look at that and say, hey, we can reduce this one more time. No, not unless you want to go to imaginary numbers. If we're adding something inside of our log, we're stuck. We can't do anything more to that. But really, what we have now is not so bad. It's a lot easier to deal with than it was. So f prime of x equals the derivative of natural log of x is 1 over x plus 2 times the derivative. Oh, how do I do this one? Hang on. Whoops. I'm trying to erase, not scribble. Okay, the derivative of the inside is 2x over the inside. I could clean this up a little bit. I'm not going to do a ton to it. And that's that with for these. So I could get a common denominator, but it honestly doesn't make my problem look any nicer. It's quite the opposite. So I'm just going to leave that. A lot of these problems, they're nice because we can do this, take this really complicated thing on the inside, spread it out, and make it a lot nicer. You can take a really complicated fraction where you need to take the regular derivative of that and use this as well. I don't know that our book goes through that section, but if you're curious, let me know. I can show you that. The last bit are other bases. So a is any real number. We can take the derivative of a to the x instead of x to the a. It's natural log of a times a to the x. And of course, if we have a u in there, you have to take the derivative of u prime as well. If we have log-based anything that's not natural log, so natural log is log base e. We just take 1 over natural log of a times u prime. So we clean that up just like we did before. So same idea. All right, let's find the derivative of a. We're going to use this rule. So it says take natural log of whatever our a is, which is 1/2, times the original function times the derivative of the inside, which is just 1/5/715. How do I want to clean this up? Negative natural log of 2 times 1/2 to the t/5/715 all over 5/715. Or we could just leave it like we had above. So, more than anything, get your formulas down, make a formula sheet for some of these. I do believe with that, we have hit all of the derivatives we're going to hit for the semester, for this course. So make sure you understand the base parts, go through the videos, go look at the chapters, make a good list of those, because the next thing we're going to do is go backwards. So we start with something where we've taken the derivative and we want to find the original function. So make sure you know your derivatives, and that will make that section so much easier. All right, with that, I sign off, and I'll see you next video.